not. I'm not. All right, so this is lecture 6, and it's week 3, and so of course the topic of week 3 is embodied energy. So let's just dip into the syllabus briefly and review where we've been and where we're going, and a couple things to touch on. After lecture on Tuesday, a student approached me, and this, not calling this particular student out, and I won't name any names, but approached me and said, "Gosh, I don't really know that much about recycling technology." And I'm like, well, great, you're in the right place. And you're not, and with any course, there are really no prerequisites for this course. I mean, the whole point is to, have, I'll stand up here and lecture and give my point of view, but, the forum, which we're about to dip into, is to, really let me know what level you're starting on. And I had another student last week say, I don't even know what embodied energy is. And, well, that's the whole point of lecture. So, again, if it's not clear, hopefully the examples we gave last week shows, what embodied energy is. And in fact, I'll give another very brief example in terms of some of the research that we did yesterday. Another example of embodied energy. And we'll hit glass today. We did plastic last time. We'll do some glass today. And then, yeah, question.
Well, when we're doing the embodied energy, you're doing the math.
Yeah.
Can we scale it down? I mean, at first to something small, so you can. Get
I see. Let's do it for sure.
Basic.
Yep.
Before making it horribly huge and having to convert and do all this stuff.
Okay.
Then you get lost.
Okay, well, no, and that also is a fantastic question. So, how would you do this on a smaller? How would you look at the embodied energy on a smaller scale? I think when the problem we did on Tuesday, we were looking at thousands of pounds and millions of dollars. But I guess I want to make I just want to make one point then before we get too much further about mathematics in general and numbers. So there was, I took a lot of math classes as an undergrad and as a graduate student, and one point that a math professor made to me once is that there are plenty of numbers between the number 0 and the number 1. In fact, there are infinitely many numbers between 0 and 1. And as long as if you can sort of grasp that and understand that, that's about all you need to know. Because I could say there are, $0, 0 pounds, 0 miles per hour, 0, whatever it is you can measure, and then I can go all the way up to 1. Now, that number 1 could be 1 pound, 1 million pounds, $1 million, what have you. And there are as many numbers as you need between 0 and 1, because in fact there are infinitely many numbers between 0 and 1. So I guess with that, don't let the big numbers scare you. They're.
I almost beat my pants the other day.
So when you see the number 4 million, is just the number 4 million kind of scary? Because right off the top of your head, you could say, well, $4 million. Well, if there were 4 million people and I had $4 million, each person would get $1. So I'm not sure how else to really go about it. I don't want the numbers to be scary, but I also want you to know that there's plenty of numbers between 0 and 1. And if you sort of start thinking about things in that sense, in terms of I have nothing or I have everything, any other number can be normalized, if you will, to something between 0 and 1.
When I see all the numbers, I get then lost with the units.
Okay, so that's another good point.
And units is my biggest problem of
okay.
That, and that's why because I really would like to have an Excel spreadsheet with that all programmed in that I can just put in a number and have it.
Oh, I see. Yeah, so the question you're asking is could you make an Excel spreadsheet to put in a number and do a conversion?
I can tell you what the embodied would be at the end.
Sure, absolutely. And so the question is, could I put together a spreadsheet that tells you what the embodied energy is at the end? And yeah, absolutely. And let's just do one quick little example since we're on the topic. And do you mind doing the gold refining project? And let's do that. We'll hop into the form in the middle. Then we will do a glass calculation, and then we'll do a little bit of garbage triage. So, embodied energy. Was this showing up? Yeah. Small example. What's the question? Okay, so let's look at gold refining. And first of all, what's the melting temperature of gold?
19 something, a little less than 2,000.
Okay, now let's do the problem. Let's do the problem sort of without numbers first. And I think what you'll see is that there's this sort of magic to algebra, and there's this magic to physics, and there's this magic to engineering where you don't even need numbers at first. Let's just set up the problem algebraically, and then we'll put the numbers in and keep track of both the numbers and the units, and it'll all fall together. So that's the melting temperature of gold. This is going to be the temperature of the room. This is room temperature. Okay, now if I want to melt gold, how much energy do I need? What's the equation that I'm going to use to figure out to take gold from room temperature up to melting temperature? Yeah.
Tm minus Tr.
Okay, so so Tm minus Tr is going to be the amount of, it's going to be the temperature difference, and then we'll turn that into energy. So, so here goes delta E equals T m, there we go, minus Tr. Why is it Tm minus Tr? Well, Tm's the bigger number, and we're going to have a positive amount of energy that goes into this thing. All right, so what else is going to affect this? So obviously energy and temperature have two different units. Energy is measured in joules, temperature is measured in Kelvin. So we need something else here. What else are we going to put in?
Time.
Time is not going to matter. Time will not matter. I mean, time does matter, but not in terms of calculating the amount of energy. Hey, Priscilla.
The source of heat.
Source of heat will not matter either. You could use the sun, you could use gas, you could rub your hands together. Source of heat doesn't matter either.
Efficiency of the kiln?
Efficiency of the kiln will matter, but but we just need to know how, like, theoretical bottom amount of energy that's going to take to melt that gold.
Ask Priscilla, she knows.
Is it going to take more energy to melt a bar of gold or a little pea of gold?
Oh, we're talking the amount of gold.
There we go. There we go. There we go.
Okay.
The mass is going to matter. And so now we've got temperature times mass. What final number do we need in there? If you remember back to 101 and 102 and 235, it's just the heat equation, the specific heat equation. So all we need is the specific heat of gold. Okay, and that's going to give us the amount of energy.
What was this heat?
That's the specific heat. And this is going to be fundamental to all these guys. So this is specific heat. heat, and this is going to be the mass, and we've got the temperatures already defined. So let's just go look those numbers up, and we'll come up with a number. We'll come up with a number of joules.
So in Fahrenheit, it's 1948 degrees.
Okay, super. 1948 degrees Fahrenheit is the melting temperature. What's room temperature? Let's just call it 70, 50, 60, whatever. Let's just call it 60 degrees. I think that's what we were yesterday outdoors. We're on this thing. Okay, so now we're gonna have our delta T. What was the mass?
3 grams.
Mass equals. So this is mass equals 3 grams equals 0.003 kilograms. Nice small numbers, right? No millions, billions
So you
flying
already
around.
put it in kilograms.
Yeah, there's 3 grams, same thing, 3 kilograms. Now, we just got to go find the specific heat of gold. C sub P comma AU. AU, give me back my gold. All right. So let's see. We'll look at a couple of things. So here's University of. Okay. So we're looking at 0.129. Sorry, 0.129. Getting dyslexic here in my old age. Now, this is also the specific heat at room temperature. Now, typically. Well, so let's look at the units here. So this is joules per gram per degree Celsius. So this means this is just how much energy that material can hold. Now, at room temperature, it has a certain value. Typically, as the actual temperature raises, the specific heat changes. Not much. But as something gets hotter, it's less and less able to actually hold thermal energy in general. But for the sake of this little numerical experiment, it might change by 1 or 2%. So going all the way up to its melting temperature, it's not going to affect the outcome. Does that make sense? Okay. So.
But even if it's molten, it still holds thermal energy.
Of course, yeah. If it's molten, it still does hold thermal energy, but not as well.
So it actually does change once it hits that point.
Yep. And there's a whole branch of thermodynamics we can go into, but for the sake of this exercise, we can just use this and know that we'll be within the ballpark. And we're using the gold in its solid state. So this is just a simple example. So 0.129. So 0.129, and what do we say? This is joules per gram Celsius, per gram degrees Celsius. So this will give us an opportunity to do a little Celsius to Fahrenheit conversion as well. And let's go ahead and take another look back here. Hyperphysics, see what they have to say. Oh, and there's the 0.129 as well for the. So I've seen that same number twice. I'm starting to believe it. 0.126, fine, all right.
At 20 degrees Celsius there.
At 20, yeah, so a little bit less. And, well, in this case, it looks like the specific heat of gold actually went up when it got hotter. So different substances will behave slightly differently. But, again, 0.03, it's in the noise. Okay, they've also got it in calories per gram Kelvin or BTUs per pound Fahrenheit. Obviously, and every single one of these is energy per unit mass per temperature. So going right back to our equation, we can see that this is in joules, this is in whatever units of temperature you want to use, this is in whatever units of mass you want to use, and then the specific heat, as long as you're using the correct units. So we'll hop on down to the next page. And let's just first of all take our degrees Fahrenheit and convert it to degrees Celsius. So,
32.2.
so delta T equals 1948 minus 60 equals, do that really quick, 1948 minus 60 equals 1800. Let's call it 1900. And you could have just done that in your head too. 1900, close enough. The mass we have, and this is 1900 degrees Fahrenheit. Now, how do we get from Fahrenheit to Celsius?
Have it into a converter.
Well, it's 5/9. So 1 degree Celsius is 5/9 of a degree Fahrenheit. So we'll just take that 1900, multiply it by 5, divide it by 9 equals, call that 1,000. And again, we're just kind of ballparking. This is 1,000 degrees Celsius. So now our delta E equals, C sub P we have, there's 0.129 joules. I'll put that in the numerator where it belongs. Here's grams in the denominator. There's degrees Celsius in the denominator. That's our C sub P. Our mass was let's go with grams since that's what we're using. 3 grams times 1,000 degrees Celsius. Put that through our little machine here. So times 0.129 times 3 equals 405 joules. Not a heck of a lot. Not a whole heck of a lot. In fact, it's tiny. Equals 405 joules. Okay. Now, how much energy did we use to melt the gold? And that will give us an efficiency on our process. Right? Okay. So, what did we use to melt the gold? Propane. Okay. So let's just go E. And what's the chemical formula for propane? Propane's 3 carbons, right? So it's C3H8 equals. We're just going to call it the specific energy. Let's just write it this way. Specific energy of propane, C3H8, times how much we used, times the volume, and we'll do it in volume. We could have weighed the cylinders too and looked at the tanks, but let's do the volume. What was the volume of that propane tank? About a liter.
Yeah, one.
Pressure. Any idea what the pressure was on that propane tank? High and low pressure, liquid. Again, we're just doing a little research on the fly here. about propane, blah, 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 propane regulation. Let's take a look at this guy.
Well, it's like 16.4 ounces.
How much?
16.4 ounces.
So, okay, 16 ounces in one tank?
Yeah.
Okay, let's go with
Is
that.
that-
That's a good
does that
start.
help?
That helps a lot.
Because I don't think I'm gonna be able to find.
That helps a lot. That helps a lot. So the mass of the tank equals 16 ounces. And how long will that tank run? Well, if you just let the thing run all day long, what's the amount of time you think you might get out of it? What's a good estimate? We're running at full blast. Full blast. Would like 4 hours be a reasonable guess? 2 hours? We ran ours for 20 minutes yesterday. And, we could do the experiment, just run the dang thing, but for the sake of argument, let's just say you can leave the thing running for 2 hours. Seem reasonable? Camp stove, 2 hours? Okay. Okay, so time equals 2 hours. So the mass flow rate, and we'll get to the volume here in a little bit. The mass flow rate equals 16 ounces per hour. Now let's convert that. Let's convert that to grams per second. So let's convert ounces per hour to grams per second. And again, nice small numbers. We wanted to do some units conversion. Here's the perfect opportunity. So 16 ounces.
Sorry, what was?
Oh, I'm sorry, per 2 hours. Yeah, my bad, 2 hours. Thank you. Yep. Per 2 hours. Now we've got how many grams per ounce? 30? 28 grams per 1 ounce. And then how many, let's see, we've got how many seconds per hour? 3,600 seconds per, sorry, let's do it the other way. 1 hour on the top, because we need that to cancel. 3,600 seconds. And again, this might be off by a factor of 2, because we're just estimating here. But we've got 16 times 28 divided by 2 divided by 3,600 equals 0.6 grams per second, or 0.06 grams per second. Equals 0.06 grams per second, or, sorry, let me close that. Or you could call that 60 milligrams per second. Okay, now if we ran it for 10 minutes, we can now calculate how many grams we used, right? So let's go, so time equals the mass flow rate, which we just calculated, mass flow rate. Oh, I'm sorry, no, let's do it this way. We know the time. What we're trying to figure out is the mass. So the mass equals the mass flow rate times the time. Pretty simple. So that equals 0.06 grams per second. And we ran it for, what did we say, 20 minutes? 20 minutes over 1, And there are, let's see, now we need to get from minutes to seconds. So from there, we've got 60 seconds per 1 minute. I think I did that correctly. Yeah. Equals our 0.6 times 20 times 60 equals. So let's say we use 74 grams of propane. Right? So now we know approximately. You know, it might be half of that, it might be double that, but this is exactly how you are going to go about calculating your embodied energy in every single recycling technology or every single manufacturing technology problem ever. And these are nice small numbers, we're not up in the millions, et cetera, et cetera. Okay, so let's just call it 75 grams. Okay, now, how much energy is that? Well, we could go, I wrote this up before as the specific energy of propane times the volume, or we could write it like this, specific energy of propane times the mass. Either one will work, because if you remember in Tuesday's lecture, we looked at energy densities, and there was that nice chart that showed energy densities either on a mass basis or a volume basis. So since we've got mass, let's just go up and look up the energy density of propane on a mass basis. And hopefully it's down here somewhere. Okay, we're not using plutonium, fat, ethanol, coal. Oh, did I? Oh, thanks. Super. Okay, perfect. Thank you. And now let's get it. We've got it in megajoules per kilogram. 46.4. Let's write that down. So the energy density of propane, H8, and I'm going to write this down on a mass basis, equals, what did I say, 46.4 megajoules per kilogram. And let's just knock 3 orders of magnitude out of both of those. 46.4 kilojoules per gram. Right? So I knocked 3 orders of magnitude out of the numerator going from millions to thousands, and I knocked 3 orders of magnitude out of the denominator going from kilograms to grams. Is that clear enough? Because if not, we can talk about it after class. But that's NRG 101 stuff. It's the same units, and kind of also going back to my initial statement about there's plenty of numbers between 0 and 1. We're just normalizing there. Okay, so I've got this in kilojoules per gram, and now I've got the amount of mass. So now all it's left to do is say energy equals the specific energy of propane, C3H8, on a mass basis times the mass of propane, C3H8, equals 75 grams times 46.4 kilojoules per gram equals 75 times 46. 3,000 kilojoules. 3,400 kilojoules. I'll just call it 3,400 kilojoules. Does that seem about right to you? That we would use 3.4 megajoules of energy to melt 3 grams of gold? Tell me if that fits with your intuition or not, based on what you know from the very first lecture of NRGY 101. What is a human's energy consumption in a day? What's it take to run one human being for one day in megajoules? Ten 10 megajoules. Yeah, each human being on the planet needs 10 megajoules to sort of run his or her own physical plant. Hey, what's going on, Sean?
And it was like 100 or 150 watts.
Yeah, that's right. Yep.
Is it 100 or 150?
It's 115.
Oh, 15.
10 megajoules, a 10 megajoule physical plant like a human being running nonstop is running at about 115 watts. But when you're sleeping, it's 60. When you're running up Mount Sentinel, it's 300. But average human metabolism is about 115 watts.
See, for Mama, I understand watts better than megajoules.
Yeah, and some people think in terms of power. Some people think in terms of energy. But it really is energy that ties all these things together. Okay, so now, so 10 megajoules equals 1 human daily value of energy. So does that make sense that it would take a human 8 hours to compete with a propane tank burning for 20 minutes? It sounds about right to me. When you look, and you remember that very first paper we read in NRGY 101, humans are pretty wimpy when they're trying to compete with combustion processes. So I would think that's about right. Now from there, we can now get an efficiency of that process, right? And now all we have to do is look at the efficiency of the gold melt, and it's always the little number over the big number. What was the embodied energy? 405 joules. And we're going to divide that by 3.4 times 10 to the 6th joules. So 405 divided by 3,400, there's 1,000, equals 1.1 times 10 to the minus 4th. 1.1 times 10 to the minus 4th equals 0.00011. Is that very efficient? Now, but where's the inefficiency coming from? What's going on when we go and melt anything? We could have been melting plastic, we could have been melting glass, we could have been melting any material that we've been mentioning so far. Where's the heat going? Well, it's escaping off into the atmosphere, right? I mean, we were doing the experiment yesterday. I would not want to have touched that kiln because it's quite hot. I think there's a couple other things that the inefficiency is coming from. Another is that, and really we've only done part of the problem, because another issue, and I think what's going on with the kiln process, is you're also putting in energy to sort of off-gas any other impurities. There are also other metals in there that you're having to melt, and I would think, the longer you cook this thing, the purer it gets, in a sense. And this is going to be also the case in any type of material unmixing process. And that's really what you're doing when you're sort of collecting materials, is you're unmixing them. And it always takes energy to unmix things. And that's true of any mining process. I mean, when you go and dig the ore out of the ground, what do? When you heat up the iron ore in the furnace, you're unmixing it. You're taking that iron out of the other elements that are there. So that's really what we're doing here. In order to make this more efficient, you might put better insulation on the kiln. You might try a different heat source. I would love to be able to do this with a lens, just straight up, just use the sun, hit that same temperature, and just forget the hydrocarbons completely, because all of those, I'll guarantee you every one of those hydrocarbon bonds were put there a long time ago by a geological process. So anyway, yeah, question.
So megajoules to watts is like 944 watts.
Now, careful about, so the question is, how do I get from energy to power? What's the equation?
Well, I don't know, I just did it for
Okay. Well, this is fundamental to energy technology. What is the relationship between energy and power?
Whatever times hours.
Yeah, time, exactly. Yeah, exactly. So if we want energy and we have power, all we do is multiply by time. Yeah.
So I could take that watts and then say that the tank costs $3.99.
Mm-hmm.
I could figure out how much cost of propane I do.
Absolutely, yeah.
Takes 20 minutes.
Right.
Do it that
And
way.
figure out whatever fraction. Yeah, so you could do it on, so we just did it on an energetic basis. You could also do it on a dollar basis.
To me, dollar S is more important.
Okay, yeah, well, of course.
No.
Yeah, of course it is. So if the tank,
But we had two tanks.
oh, so we just multiply it by 2.
Yeah.
Sure. Well, so in fact, we did have 2 tanks, so we would take that number and divide it by 2, so our efficiency just went down by a factor of 2. But yeah, if the tank cost equal, let's just say $5, and we decided that we ran it for 20 minutes, or what would that be, 1/6 of its lifetime, 1/12 of its lifetime. So whatever 1/12 of $5 is.
Why did you get 112?
2 hours divided by 20 minutes.
Oh, that's right, because we did.
Yeah. So the tank costs $5, and then the experiment cost equals $5 over 12. Somebody help me out here. 5 over 12 equals 41 cents. Okay, now, so from a thermodynamic perspective, this was a very inefficient process. From a corporate, capitalistic, greedy perspective, it was a very efficient process.
So what did,
Because we refined $100 worth of gold for 50 cents.
so wait a minute, no, what did you do, 10? What you did, the garbage cans are away.
Oh, I'm sorry.
It's not, it's like show and
Okay.
tell. It's like a show and
All
tell.
right, well, change that number, because that's one, say, if one tank was 5, but you had 2 tanks. So actually, let's do.
Oh, okay, change the number, sure.
Let me be more. That's
82 cents. Oh, sorry, not $82, yeah. $0.82.
Okay, 7.
And so and thus your financial efficiency also was knocked in half, because you spent 82 cents to refine that $100 worth of gold, but Financially, that's, pretty good. Now, we didn't count for time, whatever the labor would have cost, and we walked in today talking about what are the labor costs of standing there or anything.
Is that 682 you got, or was that 82 cents?
82 cents.
Okay.
Yeah, that's a zero right there.
What did you divide by 12?
I divided by 12.
Should have been 6.
Oh, you're right, it should have been 6. I'm sorry. Yeah, it should have been 6. Good question. Why divided by 12? Well, because I was thinking too quickly and not carefully enough. We estimated that the propane tank would run for a total of 12 hours, and we said we ran it for about 20 minutes. So there are 6 20-minute time frames in 2 hours. So thank you. Good. Good, man. This is a team sport. I'm liking it. Thanks for being engaged. Was that your question? I mean, that's where it came from. Oh, I'm sorry. Yeah. So we started out by saying that the propane tank that was used in the refining experiment, and this is just hot gas coming out of a tank and melting gold. We estimated that it has a mass of about 16 ounces, and we estimated that 16 ounces running out of that tank at full blast, it would take about 2 hours to completely exhaust the tank. And from that, we got our mass flow rate, and it came out to be 60 milligrams per second, okay? And then we ran our experiment for 20 minutes. So we had the tank on for 20 minutes, and that 20 minutes is 1/6 of the lifetime of the tank. 20 minutes is 1/6 of 2 hours. Is that, okay.
Okay, so if we redo the math then.
Redo the math, yeah, we can double it again.
What did you do?
I just doubled it. You just take that.
Double
Instead of divided by 12, divided by 6, it just doubles our percentage, basically.
Yeah. Where was that guy again? So, right, so we can change it right here. Turn that guy into a 6. So my arithmetic errors aside, the method still stands. 0.82. And so we're looking at a buck, what is that, $1.64? Hopefully I can still divide by 2.
How do you get the $1.64?
2 tanks.
Oh, 2 tanks.
82 times 2 is 164.
See, I put the 2 tanks down at where the $5 was.
Oh, wasn't each tank $5?
Each tank.
Yeah.
So that would be $10.
Yep.
10 divided by.
If you had 4 tanks, you just double it again. If you had 8 tanks, you double it again because you're burning it that much faster.
It's $1,
Yeah.
$1.60.
Well, so the economics are still pretty good. We invested or burned or used or whatever $1.64 worth of propane to obtain $100 worth of gold. Now,
What is XP?
one sec.
EXP.
Experiment.
Oh, XP.
Oh yeah, the cost of the experiment. So, running the experiment cost that. In our case, it was an experiment. But if you were doing this from a commercial venture, it would be your cost of doing business. It would be the whatever you're spending on that refined fossil fuel to run your operation. And so this is very similar math to what we just did for the plastic. And we decided we're going to have to invest that half a nickel to take the value of that plastic from 3 cents a pound up to 6 cents a pound. Okay, so I'm going to throw this back to you. How much embodied energy did we add to that goal? I mean, it's sitting right here, right here. We put an extra 3.4 megajoules of energy into that goal. Where is that energy? Well, some of it's still floating around in the atmosphere of heat, and some of it, in a sense, is still embodied in that gold, because that gold is now a purer substance than it previously was. And and it's the same. If you were to make a tank of oxygen, let's say, so most of the medical oxygen that people use, where does that come from? It comes from just squishing the heck out of air. If you just take air and compress it and compress it and compress it, eventually the air will turn to liquid. And in fact, inside the propane tank, that propane is also in a liquid state. So if you just keep compressing air, eventually you will get liquid nitrogen and you will get liquid oxygen. And so you had to put energy into that air to get out the oxygen, the nitrogen, some water is going to come out. So same thing. There's embodied energy. That's exactly what embodied energy is. Does that make sense? And there are varying degrees of efficiency in that embodiment. And and that's typically why higher carats of gold are more expensive, because more energy had to be put in to get the other crap out. Make sense? Okay. So we looked at it on an energetic basis. We also looked at it on a dollar or economic basis.
See, I would like to have an Excel spreadsheet, so I could put in, let's say, 6 grams, and it would tell me how much it costs with propane.
Let's do it. We'll have to do that offline, but every one of these little equations that we scribbled out by hand would be very readily doable in an Excel spreadsheet. And in fact, that skill, and if you take ETEC 214, energy storage and distribution, we do that all day long in 214. We make spreadsheets to kind of repeat the same exact scenario, model, what have you, all day long. And we do it in joules and we do it in dollars. And I guarantee you, this is the same exact math that every single petroleum company on the planet is doing right now. I mean, how much energy it take to build the rig, to pay the guys, to drill the hole, to pump it out, to refine it, to get it to you, et cetera, et cetera. And so far, they're winning. They're sort of dominating just because of the readily available supplies that we have. That's changing. It's changing very quickly. Okay, let's take a pause there.
But this is all true cost aside.
What do you mean by true cost?
We're not taking into account the environmental impact.
No, that's right. We're not taking into account the environmental impact, and the numbers are across the board in terms of what it actually costs the environment per se, and that's a whole different philosophical discussion. Yeah. All right. Well, that was good. We have a better grasp on what embodied energy is, and we looked at efficiency both from a thermodynamic standpoint and from an economic standpoint.